Hi everyone. In this video I'm going to talk about sampling error and margin of error. And I'm going to do so in the context of building out of confidence intervals. Okay, so when we build a confidence interval, we're specifying the reliability associated with our estimate of a population parameter, generally the population mean. So we say this estimate is accurate within a margin of error, which is equal to half the confidence interval, because we could have been overestimating or underestimating the true value. So we've targeted the true value of the population mean within some margin of error, which extends to the bounds of the interval, going half the length of the interval in both directions from the center, which is just the sample mean. So at this point, we should be thinking about the effect of sampling and the effect of sampling error and randomness on our estimate of the population parameter using the sample statistic. And we want to pay close attention to this when we're assessing statistical significance. So what's the point? Well, the point is, for any particular sample we've drawn, when I realize we could have some other sample drawn in its place, and any other sample would necessarily have a different sample mean. Of course, repeated sampling would construct a distribution of sample means, the sampling distribution of the mean, which we saw as approximately normal by the central limit theorem for large samples. The sampling distribution has some mean. It's just the population mean in expectation, and it also has a standard deviation. That's the standard error. So we can use the sample size and the standard error to compute the probability of seeing a particular sample mean. So for example, suppose we've drawn a sample of 150 births of newborns in Pittsburgh. Suppose we know the average weight for a newborn in Pittsburgh is 6.5 pounds. Suppose this is some known average, therefore it's a population parameter, the population mean. But suppose in our sample we get a mean of 7. So we wonder if the true mean is really 6.5 pounds. What's the probability of selecting a random sample from that same population but finding a sample mean of 7 pounds? In particular, what we're asking is that half-pound difference statistically significant? The underlying question is essentially, is the sample mean too far from the population mean to have arisen by random chance? That's the sampling error. Is it too far away from our supposed population mean to have just happened by random accident from sampling? So to answer this question, we need to think about sampling error, the random chance inherent in sampling. For the sake of the example, I'm going to assume the sample standard deviation is 1, so the standard error is just 1 divided by the square root of 150, which is 0.082. So now we can go find the t-value and determine the approximate probability of getting a sample mean by chance when the true mean is 6.5. The formula for the t-distribution is just the sample mean minus the true mean divided by the sample standard deviation, or 6.097. What's the point? Well, if we have a sample of 150, we have a sample of 150, so we're going to compare this test statistic, the 6.097, to the t-value associated with the distribution with 149 degrees of freedom. So that's not on our table. The table is going to classify everything from 120 degrees of freedom and above as being the same, with assigning a critical value of 3.291. So the probability of getting this particular value of 7 pounds when the true mean is 6.5 pounds, so essentially the probability of getting a t-value of 6.097 is less than 0.001. So what I've done here is actually compute a p-value. We discussed this in class. The point to mention this now is just to point out a tie-in. The p-value, of course, is the probability of attaining a test statistic at least as extreme as the one we obtain, given our assumption of the true mean. So that's basically what we just computed in this example. We showed it's very unlikely to have attained this test statistic from a simple sampling error alone. 95% confidence intervals will correspond to p-values of 0.05 and 0.01 respectively. We've clearly found a much smaller p-value. So now, going back to margin of error, turns out that our confidence intervals are just of the form of an estimate plus or minus a margin of error. That's another way to interpret the bounds of the confidence interval. It's just the product of standard errors times the critical value. The margin of error tells us how accurate we think the sample statistic guess for the population parameter is. Suppose we want to get a smaller margin of error. We want to get a more narrow confidence interval. We can do this by decreasing the confidence level, or by increasing the sample size, or by drawing from a population with a smaller spread. The point is, we want to try to collect our data intentionally such that we can get a small margin of error and a high confidence level. In other words, we try to get a large sample size in order to make this happen. That's what we have the most control over. But how large is large enough? Well, we have a formula which relates the sample size to a given margin of error. So we just begin at the definition of margin of error, which is the product of a critical value and a standard error. And we solve for the sample size algebraically. So here's a quick example. Suppose we have a standard deviation of 45. We want to be 90% confident that the mean is within plus or minus 5. Just plugging in these values, we determine that the requisite sample size is just 220.